In this video, we're going to take a look at high pass passive filters. As the name implies, this filter is going to be designed such that it will pass the high frequency above a certain point called the cutoff frequency, and it will prevent anything below cutoff frequency to go through. As far as analyzing, it's very similar to earlier video that we did with low pass filter. You've got a resistor, you got an inductor, and the output voltage will be taken off the inductor, and the input voltage would be the voltage that comes in. So we got a certain amount of frequency, a certain amount of signal with certain frequency comes in, and what's going to happen is that the output will have only the high frequency content and not low frequency content. So again, we know that the Z for an inductor is J omega L, as we discussed earlier. S is basically J omega. And then simply to solve this is we do a simple KVL around the loop, find the current, and then we find V out in terms of the current times I J omega L. After we clean it up, we'll end up with an equation that looks like V out over V in is equal to J omega or S over S plus R over L, and that would be the transfer function for it. Now, the next step is to find where this cutoff frequency, this is omega C is referred to as a cutoff frequency, because if you take the magnitude of H of J omega, which is the magnitude of the numerator divided by denominator here, and as the omega increases, the filter starts to pass more and more until it gets to the maximum 1. For 1, one means all the input is getting passed to output, so the ratio of V out over V in is equal to 1. And that's the maximum, as we know, for this. And then once it gets to 1 over square root of 2, that basically puts us at half power. And that's how we determine where omega C, or the half power frequency, is. Okay, so again, as long as we're doing this, we're also going to draw the phase for these filters, and then omega C, once we set the H of J omega to equal to 1 over square root of 2, that would give us the J omega C, because that J omega C is the only time that value will occur. And that will tell us that omega C, once we clean that up and solve it, omega C is equal to R over L. We take on that and plug it back into this equation, which tells us the transfer function, the full transfer function, can be written in terms of omega C. Again, this way of writing, it's called implementation independent, because there's another way we can find we can design a filter using RC. The equation will be the same way, except the omega C will change. So let's go ahead and take a look at if somebody wanted us to design a filter using R and C. Here's how you would design it. You've got the input coming in here, your capacitor sits in here, and your output comes off the resistor. And again, if you do a KVL and do some cleanup, you will end up with V out over V in equaling this quantity. And as you walk through the same process to find out omega C, you will find out that this is omega C. Therefore, you can write the transfer function in terms of omega C, as long as you know omega C is 1 over RC. Again, R1 over RC, as you know, RC was the time constant, so it's 1 over time constant. And for a LR, if you remember, R over L, L over R used to be a time constant, so this is 1, omega C is 1 over time constant. So there are some things that we can leverage from what we have learned before. But one thing I wanted to notice is that in this case, the voltage is coming off the resistor. In this case, the voltage is coming off the inductor. But either way, as long as you make the appropriate determination of omega C, the transfer function for both of them are the same. Just a reminder, the transfer function is what relates V out of S to V in of S. That is what tells us if you give me V in, I'll multiply it by H of S, and that gives you V out. Okay, that brings us to the end of the high pass filter. Before we go away from this, I wanted to also just remind you that if you were doing a low pass filter, if this low pass filter would just looks just like this, except the V out for the low pass will come off here, and high pass comes out of here. Same thing here. If you look at it, here is the high pass output, and if you want the low pass output, then you can go ahead and get it from here. So if you go back and listen to the video for the low pass filter, you'll see exactly the same circuitry, just where the output comes out is different. So these filters are very interrelated and connected, and it's important for you to kind of make those connections between the different types of filters.